Hey, what's up, guys? This is Chung here. So this time, LeetCode number 882, reachable nodes in subdivided graph. Okay, so apparently this is a graph problem, right? So we're given like graph with n nodes labeled from 0 to n minus 1, and then we want to subdivide each edge into in the graph into a chain of nodes with number of the new nodes uh, based on the count of these edges. Right, so what does it mean? It means that, for each edge, right? So for each edge like this one, from U to V, right? We have U and we have V. This is the edge, right? So if for U, V and a count, so let's say if we have a count equals to 2 here, it means that we're gonna add 2 more nodes in between these 2 nodes and into this edge like this. Okay, right? If it's 0, it means that there's no new node. That's that's it, right? Okay, and then okay, so we have the edges here and we have the nodes n here, and we also have like this max moves here. So max moves means that our task is in this new graph, right? After dividing each node based on this count here, we want to know how many nodes we can reach, right, within this max moves, right? So what does it mean? It means that let's say we have many nodes here. Let's say we have a lot of nodes here. Okay, so let's say the max move is 2. Okay, it means that we can only move max to 2 nodes first, to 2 nodes, right? Let's say the max move is 3 here, right? So it means that, from here to here, we start from 0, right? So reachable from 0. So let's say this is node 0. Let's say we have another node here, okay? UV K here, right? So as you guys can see, we can reach what are the nodes we can reach? This one is fine. This one is fine. This one is fine because to move to this node, we only need 1 move, right? To move to here, we need 2 moves, right? But how about this node in between here, right? I think we can move reach to this one, this one, this one, because that's a 1, 2, 3, right? So these 3 are fine, and this one is also fine. And why is that? Because we can reach this one from this path, 1, 2, 3, and 4, right? But for this one, no matter which way we go, we'll never be able to reach this one and with this max moves, right? So that's why the total is like what? 1, 2, 3, 4, 5, 6, 7. So the answer for this graph with this max move equals to 3 will be 7, right? I think that's what basically this example 1 is telling us. For this one, we have like from 0 to 1, we're gonna add 10 more new nodes in between, right? And for this one, we have 1, and then we have 2, right? So that's that, and we have some like basic constraints here, right? So for this kind of graph problem, since we want to know if we can reach this node within this max moves, it means that if there are multiple paths that can reach this node, apparently we're gonna take the shortest path, right? Then which leads us to like the shortest path algorithm, which is Dijkstrom, right? Basically, the Dijkstrom can tell us the the what the shortest distance, right, between 0 to each node, right? And then for this one, the weight will be the count, right? It means that basically from 0 to 2, right? We need to use the weight will be 1, right? But actually it should be 2. It should be 1 plus 1 because this count this the third parameter here is the new node. It's the new node we added in between, right? But to reach to 2, we need to do a plus 1 to make it the real weight, right? Because with one more node here, we need a 1 plus 1. We need 2 moves, right, to move from 0 to 2. So this is one thing we need to be careful when we create the graph, right? So So what we should do is that, let's forget about this split here, right? Let's only consider this one as a weight, right? In that case, we can easily use diagram to calculate the weight, right? The weight for each of the node, given, sorry, the shortest path for each of the node. Okay, and then with that, we can then try to calculate how many nodes we can visit in between those, right? And how can we do that, right? So let's say we have this one, we have this 0, right? No, we have this one and we have this one, right? They're like, let's say they're like 10 nodes in between. Okay, so this is U, right? And this is V, right? So for each of the edge, so let's say the distance, right? So the shortest distance for U and V. So the first scenario is what? If both of them are greater than the max move, right? So if that's the case, then apparently we cannot visit any of the nodes in between, right? Second is what? Second is actually, there's second is that basically it will be either of them will be within the max moves, or both of them will be in the max moves. So in this case, we have several scenarios. Basically, we can reach any of them from left, from right, or there could be overlapping, right? So in this case, there's no overlapping between the left and right. So this one means that from left we can reach 6, right? And from right we can reach 1. In this case, 7 is fine. But what if there's some like overlapping? Let's say from the left we can reach this part, and from right we can reach this part, right? Then there's some overlapping. So apparently we can just simply use the left, the minimum of the left and the right, right? And also what? Left plus right, and then the weight here. Weight is basically it's a node in between. Yeah, I think that's it, right? So basically by using this kind of a shortest path, right? And what is the left? Left is the maximum, max minus the shortest distance, the distance of u, right? And the right similarly is the max minus the distance of v, right? So that's the basic idea here. Yeah, so that after calculate, so that's the way how can we count the node in between the node, in between the edge, right? Yeah, let's start coding, right? Let's write the Dijkstra algorithm first. So for the Dijkstra, we need we need the graph, right? So it's gonna be a list. So for u, right, we have u, v, and we have weight, right, in edges. Okay. So for graph, we have a u dot append, right? So like I said, here when we create the weight for each node, for each edge, we need to do a w plus 1, right? Because that's the w is a new node, and to be able to transfer it into moves, we need to do a plus 1, right? And then we have a similarly thing for v here, right? And this time it's gonna be a u w plus 1. Okay. And then we have a distance, right? So we have distance for each of the node between each node with the node 0, right? So at the beginning, everything is the biggest, and then we have this one is at the beginning 0 to 0 is 0, right? Then we have priority queue, right? So priority queue is like this. So for Dijkstra, so the first one is the current distance, right? To node u, right? And then we have what? So let's do the Dijkstra first. So while priority queue, so we have the first one is going to be the weight, right? It's going to be the weight. Second one is going to be the node, right? So remember, we need to put the weight, the current distance. Yeah, actually, let's call it distance, okay? maybe distance is better. So yeah, weight or distance. You can use either one. So we have distance here, right? Uh, put the distance into the first one so that we can sort, right, by the distance. And then we have heap pop of the product queue, right? And then for V, and then we have the new distance, okay, new distance in the graph of V of U, right? So this is all part of the Dijkstra template. So if the D plus the new D is smaller than the distance of the V, right? And then we so first we update the distance of V to this D plus new D, right? And then second we push this new distance, right? D plus new D distance. Actually, this is the next distance, right? Along with a V into that priority queue. Okay. So now after this while loop, after this Dijkstra, we have the shortest distance for each of the node, right? And then let's check the edges one by one, right? So we will U V W, right, in the edges. Okay. So first, like I said, so if the distance of U, right, is greater than the max moves, and the distance of V is also greater than the max moves. Actually, you know what? So for this one, we need to first count if we can reach the current node first, right? It means that if the distance of U, right, is within the max move, right, then the answer will be, oh, we need the answer here, right? Be 0, right? So if this one is gonna that, right? Similarly, right, if the distance of V, right, smaller than the max moves, right, and then we need to do an answer plus 1 again. So these are the like, oh sorry, I actually we cannot do this here because same U and V might be appear in this edges multiple times, right? So we cannot do this. So we have to do it at the very beginning here. So for U and W, right, in edges, okay, so basically something like this. Not in edges, sorry, in the distance. Okay. Yeah, in distance it's gonna be enumerate, right? Yeah, so that's why we need to remove this part here. Like I said, we have to enumerate the distance instead of edges, right? So now we have already counted all the original node we can reach, right? So the next thing will be to check the edge, the nodes in between each edge, right? So like I said, the first one is like this. So if this one is that, we continue. It means that there won't be any edges. At the start, there won't be any nodes in between that we can reach, right? And then let's do a count one, right? And then actually I use the left and right, right, while I was drawing the diagram. So I actually should be there's no left and right. Instead there should be a count one or count two. So count one equals to this, gonna be a max of moves. Oh, actually let's do this. Max moves minus distance of U, right? And then we have count two equals to the max moves minus distance of V, right? Now, like I said, we do this, right? Minimum of count one plus count two and this W, right? In case there's a like overlap. So this one means that, if there's overlap between the count one and count two, we do a minimum because the maximum we can add is this W, right? But here, since since this distance of this u could be greater than the max movement, so which means that either count 1 or count 2 could be negative values. So to make sure it will not affect our final answers, we should do a max of 0, right? So which means that if we cannot reach this u here, right, then this count from this side will be 0. Right? Similarly for this count too. Okay. Return answer. So I think that's it. Yeah. Okay, so let's run the code. Default. Oh, did I? Default. Okay. Okay. Priority queue. Okay. Okay, cool. So it works, right? So as you guys can see, so this is like just a little bit of variation of a standard diagram, and so that's why the time complexity for this one is gonna be same as the diagram, which is e times log v, right? So that's the edges, the number of edges, and then log of v is the number of nodes, which is gonna be n, right? So in this case, yeah, because that's the Dijkstra algorithm, and here it's just like the two for loops, right? Cool. Yeah, I think that's it, right? I mean, as you guys can see, so this one we start with a very basic Dijkstra, right? To calculate the shortest distance between for each nodes, right? Between each node and 0, and then with those shortest distance, up for two side of each edge, we will be able to find out how many nodes in between we can reach, right? And then so we just so first is that when we create the graph, we do a w plus 1, right? In the end, when we do the count in between, we do a little bit of manipulation here, just to handle that overlap case, right? Yeah, I think that's it. Okay, thank you for watching this video, guys. Stay tuned. See you guys soon. Bye bye.